Hello everybody, and welcome to my talk on local intrinsic dimensionality and graphs, in particular graph embedding. My name is Miloš Radovanović, and this is joint work with my colleagues Miloš, Savić and Vladimir Kurbalija from the Department of Mathematics and Informatics at the University of Novi Sad. So as for the outline, after the introduction, I'll talk a bit about the notions of LID and graphs, and our proposed measure NCLID, which expresses local intrinsic dimensionality on graphs directly based on natural communities. And then we will apply this to improve the well-known graph embedding algorithm Node2Vec. And of course, afterwards, we will show the experimental results and some conclusions in future work. So the notions of intrinsic dimensionality and dimensionality reduction are, as we all know, pretty important. They can help us deal with the curse of dimensionality for similarity research, machine learning, data mining, and so on. However, many methods for intrinsic dimensionality estimation work on the whole dataset to express the intrinsic dimensionality as a number, one number for a set of points, which may not always be so useful. This is where the notion of a local intrinsic dimensionality comes in, or LID, which characterizes the complexity of data space around a data point, one data point. And similar work on this was done by Michael Hole in 2013 and onwards. And his notion of LID is based on the distribution of distances to a specific point of interest. And then this work and estimators of LID based on this were applied to various tasks like clustering, outlier detection, deep learning, and so on. We are interested in graph embeddings. What is a graph embedding? It is a way to map nodes of a graph to vectors in a d-dimensional vector space in a way to preserve some property of the graph. And what is usually considered important, and which we are also interested in, is preserving graph-based distances, and in particular the neighborhoods of the nodes. So we want the neighboring nodes of the graph to be mapped to vectors which are close together in the embedding space. And why would one want to do this? Well, one reason is to apply this whole universe of existing methods for machine learning and so on to graphs, which wasn't possible before. So like clustering, node classification, and so on. And also similarity search can benefit, especially since graphs, real-world graphs often have the small world property, which makes the distances be integers and not so many unique values to be present. So these distances can be kind of smoothed out when we embed the graph. Why we do this and how do we contribute? Well, we want to explore applying the notion of LID to graphs, and in particular graph embedding, which wasn't done very often before. The graph embedding, it wasn't done before, as far as we know. And we contribute by proposing a new measure, NCLID, for nodes in a graph that is based on their natural communities. So we estimate the intrinsic dimensionality of a node in a graph directly. And then we propose two extensions of the well-known Node2Vec graph embedding algorithm, which rely on NCLID. So existing LID models and estimators, they work basically on tabular datasets, on data points in Euclidean space. The theoretical model assumes continuous distance distributions, so that's why these values need to be estimated. And they're usually estimated based on distances to the k-nearest neighbors of a given data point. So we have the maximum likelihood estimator, and we have an improved version called tight estimator. And this is the formula used to compute the maximum likelihood estimation. So xi's are distances to the ith neighbor of a given point, and then this quantity is computed, and that is the LID estimate for the given data point. So how can we apply this to graphs? Well, there are two ways basically. We can take a graph-based distance measure like the shortest path distance, and then simply apply an LID estimator on that and hope for the best. And we can map the graph using the graph embedding method to an embedding space, and then apply an LID estimator there. And we are interested in the first approach. However, the first approach has some challenges if you want to do this directly. First, theoretically, LID assumes distances which are continuous and that have a limit as we tend to the point in question. And that limit is 0 for distances, obviously. And if we use some graph-based distance like shortest path distance, this simply does not hold true. So applying LID estimators to such distances is not very useful. Also, real-world graphs, as I said before, tend to have the small world property and also tend to have hubs, highly connected nodes. These can also cause problems. Shortest path distances are not only integers, there will be a small number of such unique integers. And also for hubs, LID estimates could be pretty much 0 or close to 0 because many neighbors of hubs are actually direct neighbors, and many points from the same surroundings, same community, will be direct neighbors at distance 1, right? So this is why we are proposing this NC LID measure. But first, we introduce a more general framework for graph-based LID-related measures, whereas in Euclidean space or distance space, we have a ball around the data point, and here we observe a subgraph S around node N, where S can be any subgraph containing node N. So we abstract that away first. And also we abstract away the distance. So we'll just call it dist. So once we have this, this will be our graph-based LID measure, which is somewhat analogous to the Emily estimate we saw before. Here in the numerator, here we have the number of nodes in the subgraph S. And in the denominator, we have the number of nodes at distance less than or equal to the maximal distance from N to nodes in S. So what it means is if we have this GBLID measure for node 0, this means that the distance can perfectly separate this subgraph from the rest of the graph. So all nodes that are at distance smaller than or equal to this maximal distance will be in the subgraph, will be in this neighborhood, and the rest of them will be outside. However, if this value is higher than 0, then that implies that there is more going on, more local intrinsic dimensionality, more complexity in the subgraph. So the NCLID measure is actually an instantiation of this GBLID, where for the subgraph we use natural communities. That is a well-known notion from the field of complex networks. And for the distance, we simply use the shortest path distance. So what are communities? They're basically dense subgraphs. There are densely connected nodes with each other and sparsely connected with the rest of the graph, like clusters and graphs. And natural communities are usually identified from a given node, starting as a seed, and then using some sort of search or fitness-based algorithm. We use the one by Lanki-Chianetti. So if NCLID of N is 0, then it means that the node N has a convex natural community, like a sphere, more or less, around it. And higher NCLID imply more concave, funnily shaped natural communities. So what we want to do now we have this, is to produce better graph embedding algorithms by personalizing them. That is, adjusting what they do for nodes, certain nodes or pairs of nodes, depending on the NCLID measure. And our main premise, our main hypothesis, is that nodes with high NCLID will tend to have higher link reconstruction errors. So basically, if we take a node from the original graph and that same node in the embedded graph, the neighborhoods from the two will tend not to match so well. The embedding algorithm will tend to make mistakes for high NCLID nodes. And so here's some notation. G is a graph, E is an embedding, precision recall on the F1 measure, all very well-known measures for a particular node where we compare the two neighborhoods. So node2vec is the method, graph embedding method we focus on. Here is basically how it functions. So we have a starting graph here, and then it performs random walks on it and generates these sequences of visited nodes, which are treated as sets, basically, or vectors, 0, 1 by vectors of length v, which is the number of nodes in the graph, and they're fed into the input layer of the skip-gram model, which can be viewed as a neural network, which has this input layer of length v and the hidden layer of length n. This will be the embedding dimensionality, and it's taken to be a number which is much smaller than v, obviously. So when this network is trained, what basically it does is for a given vector of zeros and ones in the input, it will give real valued vectors and the output. So if we input, let's say, a vector that represents one node, like has a 1 in one place and zeros everywhere else, it will output a real valued vector here. And the point is that for two nodes, if they appear frequently in the same random walks, they will tend to have output vectors that are more similar or less distant. Now, what we're most interested here is the way node2vec performs those random walks. And it does that in a biased way, unlike its predecessor, deepwalk, which was unbiased. So let's say a random walker has just walked from node T to node V here, and is now considering where to go next. It has, in this particular case, 4 options: node x1, node x2, node x3, and back to node T. So the probability, the unnormalized probability of transitioning to a particular node is given by this expression here, where this W is just the weight of the edge, and we assume it to be 1. So this alpha here is interesting, which depends on 2 user-defined hyperparameters P and Q. So depending on the relationships between T and the nodes under consideration, we have 3 cases. In the first case here, the walker is considering returning to node T. And in this case, the alpha will be 1 over P. In the second case, the walker considers walking to a node which is also directly connected to node T. And in this case, alpha will be 1. And the last case is that the walker considers transitioning to a node which is not directly connected to T. And in this case, the probability will be 1 over Q. And then the probabilities are normalized to sum to 1, and the die is rolled, and the walker continues. Besides P and Q, node2vec has 2 additional parameters. These are the number of random walks, which we start from each node, and the length of each random walk. So now that we introduced all this, we can introduce our 2 extensions, modifications of node2vec, with these lovely names. I will try not to pronounce. The first one of them modifies or personalizes the number and length of random walks for nodes according to their NCLID, and the other one does this, but also personalizes P and Q for each pair of connected nodes, also based on NCLID. And how do we do this? In both cases, we take the base values of all these 4 parameters and increase them or decrease them according to NCLID. And the exact formulas are given in the paper. I'll just show the basic principles here. So for the first method, for given node n, we will increase the number of random walks proportionally to its NCLID and decrease the length of the random walks. So this makes sense since if we are at a node which is kind of has a more complex surroundings, we want to stay inside more, have more random walks, and keep them shorter. And also it's convenient because that way we kind of approximately keep the computational budget the same, so the method will not have much different runtime. For the second method, we do the same thing, plus we modify P and Q, or consider modifying P and Q. Let's say X is the currently visited node and Y is the node we want to visit. So if Y is already in the natural community of X, we will not modify P and Q. However, if Y is outside the natural community, then we will modify P by adding to it the NCLID of Y. And that way we ask the walker not to go back to a high NCLID node if we already left its natural community, so go somewhere else. And as for Q, we will add to it the NCLID of X. And that way we tell it to please stay inside the more complex natural community. We encourage it to stay in and explore more. So experimental results. Here are the datasets and some basic statistics about them. These are datasets which are pretty much standard in graph embedding literature. We have them like many sizes and properties in terms of the number of connected components, and also the average degree and the skewness of the degree distribution, which tells us whether there are lots of hubs or not. For this value of 17, it's a pretty high number, so we can expect to have hubs, and here we don't expect hubs. And when we compute NCLID for all the nodes in all the datasets and plot the average and maximal NCLID for each dataset, we get this picture where we see that there are datasets where these numbers are not so high, and then there are datasets with the higher numbers, almost 9, which you can consider like moderately high dimensional. Now, if you remember, we had this hypothesis, which we said we will support. So here's the support. We looked at the correlation between NCLID for a given dataset for every node and the F1 score, the reconstruction of the neighborhood for that node. And it turns out that for most datasets, this correlation is negative. It's not extremely strongly negative, but it's also hard to ignore, which supports the hypothesis that nodes with high NCLID tend to have higher link reconstruction errors. And we also did some Mann-Whitney U tests applied to F1 scores for high and low LID nodes, and we got pretty much the same results for all datasets, but the 3 smallest one, we had statistically significant differences. And finally, we reach the performance of our methods and the base node to vec, where we can see that our methods for almost all cases outperform the baseline node to vec. So for every dataset, one of our modifications is the overall best. And here we have these maybe different dimensionalities. This is because we tune the parameters properly for the baseline node to vec and for our variance. So to conclude, yes, this is probably the first work on connecting the notion of LID and graphs and graph embeddings in particular. We saw that this measure we introduced based on natural communities can identify where a given graph embedding method, node2vec, is weak, and it can also improve it in those places. And in future work, we have many different ideas. Here are some of them. This first one was a suggestion by a reviewer, for which we are very grateful. And it suggests that we should, instead of looking at only one community, that we should like use an expanding subgraph, expanding community from the initial node, and that way we can get potentially better estimates of LID. Also, what we have been looking at already are correlations between SCLID and some other LID value scores and some other metrics on graphs from the field of complex networks, like centrality metrics, and there are some interesting observations there. And also, we worked with node2vec, which proved pretty convenient because we could manipulate its parameters. But it was also kind of limiting because what we really wanted to do was guide the random walks based on natural communities which we found. And with node2vec and parameter manipulation, this can be done only indirectly. So what we would like to explore, and we did actually start exploring it, and we have some promising results, is to leave the framework of node2vec, but stay in the world of random walks, and guide the random walks directly using the notions of natural communities. So should you leave, should you stay, or should you go, and so on. So thank you for your attention and watching this video up to the end, without skipping, hopefully. This work was done within the project called Graphs in Space. We have a website you can visit, and a nice logo, and some social networking accounts, funded by the Science Fund of the Republic of Serbia, Serbian NSF, for which we are also grateful. And once again, thank you very much.